Okay, then welcome back after the break. And the idea for today's exercise session in the electrical engineering course is if we take a look at our exercise schedule, we are somewhere here at AC circuits and complex power. So the idea is to take a look at this task 28 about complex power. And it's quite a long task, but at the end, I think there's not so much of calculation to do, but there's the circuit. And what I will do is I will, as usual, copy the circuit, put it into my drawing program, which I've prepared here. And yeah, then we can think about these subtasks for the task 28. And the first one says, okay, we have a resistor, this has a certain resistance, we have some inductor, this has a certain inductance, and they are connected in series, as we have seen, to some ideal voltage source that has a source voltage. And so maybe I should copy these values as well and paste them into the drawing program and make it a bit smaller so that we have some more space to do something. And so the first task is, what we should do is calculate the active power dissipated in the resistor, calculate the reactive power that is dissipated or that happens in the inductor or in the inductance at the inductance L, and the apparent power of the total series connection. So I will write this here in short. What we would like to know is P is QL and is the apparent power S. So what would you suggest to do to calculate this stuff? Or what formulas, which approach can we use?
Find the RMS values of EMI.
So because this is voltage times current times the cosine of the phase angle between them, this is voltage times current times the sinus of the phase angle between them, and this is just voltage times current. And because these are the RMS values, we need to find them. We need to find what is the RMS value of the voltage and what is the RMS value of the current. Okay, so I will directly delete this question mark here once again, because the voltage, the RMS value of the voltage, how can we find this? Yeah, and we know the amplitude, we know the source voltage here, we know the amplitude, so it's 325 divided by square root of 2. And you can use a calculator, or you just know, because we discussed this before, this is the peak value or the amplitude of our mains grid voltage, and if we divide this by 2, we get the RMS value of our mains grid voltage, and that is around 230 volts. And in this case, it's also does not really matter if you calculate it with comma something or with some decimals after the dot or after the comma, because in the mains grid it's also just approximately this voltage. It's depending where you measure it and so on. There's a question. This should be the square root of 2 here, yeah. Where does it come from? Yeah. That's a pretty good question. That if we would really take the derivation would probably take too long to answer. But this is for sinusoidal currents and voltages or signals, for harmonic signals, this is the factor between the amplitude and the RMS value. It's kind of a fixed factor, and it depends on the waveform that you have. And for a sinusoidal waveform, it's square root of 2. If you have a triangular waveform, it's something different. If you have some, I don't know, rectangular waveform, it's something different. And for a sinusoidal function, it's the square root of 2. Yeah, and so if you would, yeah, I would leave it up to this, because otherwise I think we lose too much time in answering this question. Okay, so we already know the RMS value of the voltage. So, okay, current. How can we calculate the current, or how can we calculate the RMS value of the current? Yeah, we could take our usual approach here and say, at first maybe the RMS value would be the magnitude of some complex current phasor. And the complex current phasor we can get from the complex voltage phasor of our source voltage, and then divided by, it includes R. Yeah, the Z, the impedance. We could do it in a way if we say, okay, if we just take, I need to do the underscore here, if we just take the voltage across the resistor and then divide by R, this would also work fine. But the voltage across the resistor is not given. The voltage of the source is given. The total voltage is given. And so if we take the total voltage, if we want to have the current, we need to take the total impedance. And so the impedance, if we continue with the formula with the impedance, we have the source voltage phasor divided by the impedance. How to calculate the impedance, the complex impedance of our circuit here? Yeah, it's a series connection, so it's the sum of the individual impedances. So it's R plus ZL. And ZL can be written as, or ZL can be calculated as, yeah, but with the J. We really need to have it complex here. I mean, yeah, at least in this equation, if this is a complex phasor, this should be also really the complex impedance. Okay, so this is something that we could calculate in Octave. And then we have this complex value, and we could take the magnitude. Of course, if we would continue with this calculation here, we could also say, we could take the magnitude of this complex phasor. This would be just the RMS value. Yeah, I will maybe add the V source here everywhere. And then divide by the magnitude of this impedance. And then we could also say, okay, it's the RMS value, the effective value, and then the magnitude of this impedance. How would you calculate the magnitude of this complex number? Exactly, R squared plus omega L, both squared, and then the square root of this. And so by both ways, we should get either the complex current or the current as an RMS value itself. Then we can insert this into these equations, and we should get the power, the reactive power, or the real power, reactive power, and apparent power. Okay, so then let's do this calculation in Octave. I've already opened it up. I will make the window a bit smaller and move it here to the right side so that I have some more space here for typing. And now we can, at first, maybe what we need to do before starting here with Octave, we need to have our source voltage as a phasor. So if we take this time function and convert it into this complex phasor, what do we do?
Amplitude exponential 30.
Yeah, and we take, and we don't, because we want to have some RMS phasor, we don't take the amplitude, we take our amplitude divided by 2, we take the RMS value to, so 230 volts, and then multiply to EJ, and then the phase angle, which is 30 degree. Okay, and what we later on also need is omega. So how to calculate omega? Exactly. And F is given there. So it's 2 times 50 is 100, and 100 times P is 314.1 something, 1 over second, or radians per second. Okay, so then we can switch to octave, and at first maybe insert our source voltage phasor, which is 230, and then remember the exponential function was exp, and we have 1j multiplied with 30. And what would we need to do to make it correct? Yeah, we need to convert to radians. So we need to divide by 180 degree and multiply with P. Yeah, and then if you think about a phasor diagram, so something that is 230 long and has this 30 degree angle, and we should get something here on the real axis that is twice as long. I don't know. That is for sure longer than the imaginary part. So if we calculate this, yeah, we should get some real part that is considerably longer than the imaginary part, but both should be positive. So this could be correct, right? Because this fits to this phasor image that I've just drawn. Okay, so then we can continue with our frequency, which is 50, and the angular frequency, which is 2 times P times F, which is 316.16. I will maybe add the 6 here, 1.16, but it does not really matter. And now we can continue with the equations that we have here at the bottom. So the yeah, maybe I will go back to our source voltage here and really we'll call this complex, so that we can see this is the complex value, and Vs, the RMS value is just the 230. So maybe you could write it like this. Say the complex phasor has the magnitude and some phase, and this is just the magnitude. Okay. So by this way, we can also calculate the complex value of the current. But before, it might be a good idea to calculate the complex impedance. So the complex impedance is R plus J omega S. So for this, we need R first. So we can check R is 10 ohm and L is 31.83 millihenry. Milli means 10 to the power of minus 3. So then now this would allow us to write this, the complex impedance here that we have there. So the complex impedance is R plus J times omega times L. And we get 10 ohm plus approximately 10 ohm. That's why the value is this 31.83 something, that at the end you get 10 ohm as well for the imaginary part approximately. And so now if we have the what does the 1j mean? Yeah, I usually prefer to write 1j. I don't know if I've explained this last time. The thing is, if you write j, you get the imaginary unit. If you write I, you get the imaginary unit. Mathematicians would use I, because for them I is the imaginary unit. For us as electric engineers, I is the current. That's why we use J. And the thing is, if you write 1J or 1I, it will be the same. Nevertheless, if you in your program somewhere for some reason use I and j as a variable, for example, you have a loop and you count over I or you count over j. So if I set j to 3 or to 2 and I to 3, then I will be 3 and j will be 2. But one I and one j will still be the imaginary unit. So using the one j is more robust, let's say. You can never change the one j. It will be always the imaginary unit. That's the idea. And that's why I'm also using one j, but here it would not really matter, right? If we go to now it would matter because I've changed the I. Okay, so we have the complex impedance. Now we can, if we have the complex impedance, if we have the complex source voltage, we can calculate the complex current. So the current as a complex phasor is the source voltage as a complex phasor divided by our complex impedance, and then we get some value. And what we want to have from this complex phasor at the end is just the magnitude, because the magnitude is our RMS current. So the current should be the magnitude of this complex phasor. How do I get the magnitude? Square root of the real part plus this, or square root of the square of the real part plus square of the imaginary part. But this is super complicated. I mean, I can write it. Yeah, it's the square root of the real part of the complex current, and now the real part squared plus the imaginary parts. Yeah, now I'm typing. So and then the square root, and then we get some number, and there must be an easier solution for this because this is not very convenient, and the easier solution is absolute value. So if we calculate the absolute value of our complex thing, then we get the same quantity. Because this is the absolute value, this is the magnitude. And we can also try this formula here. So if we say the current is the source voltage RMS value divided by the magnitude of our complex impedance, this should also work. And if we use this, the very last equation there, and say, okay, this is like the square root of R squared plus omega squared multiplied with L squared, and then closing parentheses for the square root, we get the very same value. So now we have voltage and current as RMS values, and now we can just use these three formulas. So the power is voltage times current times, I know we see, okay, before we can do this, we need to have this phase angle. So where do we get the phase angle from? Yeah, so remember this phase angle here, the phi was the phase of the voltage minus the phase of the current. So we have a complex phasor for the voltage, and we have a complex phasor for the current. Here's the complex current phasor, and there's also the complex voltage phasor. How do we get the phase from them?
Difference in imaginary parts?
Yeah, if we take the imaginary part divided by the real part, then we get like the slope. And if we take the inverse tangent of them, arcus tangens, then we would get the angle. But there's an easier function that is called angle. If we take if we want to have phi v, the phase angle of the voltage, we take the angle of our complex voltage phasor. And this will be in radians. And we can take the same for the current. So if we say our complex current phasor, then we get the angle for the current. And now we could say, okay, phi is the difference between phi v minus phi I and then we get this angle. And now if I take this angle and convert it into degree, so I multiply with 180 divided by p. What value would you expect? What value should we get? I would just do it. We get 45. So where does this 45 come from? Do you have an idea?
90 from the inductance and 0 from the resistance.
Yeah, we get, if we take a look at our complex impedance, it has the same real part and the same imaginary part. And that's why the 45, the angle between the voltage and the current, is the same angle as the angle of the impedance. So the phi that we need to have in our equation is just the angle of the complex impedance. Right? We get the same value here and the same value there. So the phi here that we need is the same as, let's say, the angle of our complex impedance that we just calculated here at the bottom. Okay, so we have the angle, we have the RMS values. Now we can calculate the power, the real power, the effective power, the active power as the voltage source voltage RMS value multiplied with the current multiplied with the cosine of phi. Then we get this. This is has the unit watt. Then we get the inductive reactive power. It's the same equation, but just with the sine function of this angle. And then we get also the apparent power. And of course, for 45 degrees, cosine and sine give you the same result. So that's why we get the very same number. And the apparent power is source voltage times current. And here we get a bit more. We get bit. We will specify what the bit is in a second. So I will just note down the values. This is 2645 watt. This is 2645 volt ampere reactive, and this was 3740 volt ampere. Okay, questions so far? There's one.
The only one is the active power at the resistor and the reactive power at the inductance. Why did we use the whole?
Yeah, we can. That's a very good question. So this reactive power only happens at the resistor, and this reactive power only happens at the inductor. Still, at the moment we have used the full voltage and the current inside this branch, and we also get this apparent power. So we could have calculated this real power. How can you calculate the power at some resistor? Yeah, so we could say I squared times R, or we could say voltage, but now not the source voltage, just the voltage across the resistor squared divided by R. And the same is what we could do here. We could say it's the current squared multiplied with omega L, or we could say it's the voltage, just the voltage across the inductor divided by omega L. And so we already have the current, so it should be quite simple to use the formula with the current at first. So P, remember P had this value. So P I could also calculate as the current squared multiplied with the resistance, and we get the very same value. And the QL I could also calculate as current squared multiplied with omega times L, and we get the very same value. So we could also try out the next equation here with the voltages. How can I calculate the voltage across the resistor. And how can I calculate the voltage across the inductor? So voltage across the resistor and voltage across the inductor could be calculated by which way? Well, using a voltage divider, for example. So, and we have a total voltage, we have a partial resistance, we have a, or partial impedance, total impedance. So how would you set up a voltage divider rule?
V source.
V source, the total voltage multiplied with the partial impedance, which is R, divided by the total impedance, which is just our Z complex here from the bottom. And so then we get this as a complex thing and this also as a complex phasor. So here we could also say complex voltage phasor multiplied with the omega L divided by ZL, and then it should be also J omega L. So we can try this out. I will maybe move my Octave window here to this side and make it a bit smaller. So we can say the voltage across the resistor as a complex phasor we get from the source voltage as a complex phasor multiplied with the resistance divided by the complex impedance. And we get some value. And then we can also do it for the voltage across the inductor. Take here J times omega times L, and I should be careful to use one J because I've overwritten the other J. And then we get some voltage across the inductor. If I take the sum of these two voltages, what should happen?
The entire voltage.
I should get back the source voltage. So I can try this out. This is the source voltage. Has this value. If I take VR complex plus VL complex, what happened now? VR complex plus VL complex. Okay, I get the very same value as before. So this works. Yeah? And so now we could also say if we go back to these equations, if I want to calculate back the power, now the power could also be calculated by the magnitude. Yeah, here it's not the complex phasor anymore, here it's just the RMS value, and the RMS value is the magnitude of this complex phasor, the magnitude squared divided by the resistance. I should get the very same value, and I get the same value. And so if I do this for the QL, now I need to take the VL voltage and divide by omega and divide by L. And I should get the same quantity for the QL, and it works. So there are many ways to calculate this. And yeah, the real power really only happens in the inductor, and the imaginary power only happens the reactive power only happens in the inductor. Real power in the resistor, reactive power in the inductor. So here we use the total voltage, but we also use the cosine term. Here we only use the partial voltage and the resistor and no cosine term. And what we could also do to add to the total confusion is we could say, okay, we take the voltage squared times the impedance, and this is just the RMS value, this is also just the magnitude, and then use the cosine term as before. Or we could say it's the voltage squared divided by the impedance and then also use the cosine term as before. Yeah, and I mean similar stuff here. And we can try this out. I don't know where to move the window anymore. So if we want to once again calculate the power and say this is the current squared times the impedance. I don't know if we had Z yet. I don't think so. We just had the complex Z. And so I need to take the magnitude of this complex Z as this Z here and then multiply with the cosine of phi, and we get the very same value. And so as you can see, you can there are many ways to do this. V source squared divided by this impedance multiplied with the cosine of phi also gives us the very same value. Okay. Does this answer your question? Okay. Would there be another way to calculate this apparent power? Instead of using the product of current times voltage? Yeah, so we could do P squared and QL squared and then take the square root of it. This should work. And we can try it out. So this was S. And if instead of this we use S as the square root of P squared plus QL squared, and we get the very same value. Yeah, and what would also work is if we take I squared times the total impedance or voltage, source voltage squared divided by the total impedance. Both of these formulas should also work and give us the correct result. So if we try this out, S as current squared multiplied with the absolute value of our complex impedance, then we get this S, and if we take the source voltage or the RMS value of the source voltage squared and divide by the magnitude of the impedance, we also get the same apparent power. Okay, so many ways to do this calculation, and what we have now very often successfully done is on very many different ways we have calculated the active power dissipated in the resistor, the inductive reactive power at the inductance, and the apparent power of the series connection. Okay, what we can do next is calculate these complex powers at the series of R and L, its real part and its imaginary part, and the magnitude, and compare this with the values that we have before. So I think I have some small space left here that I could use for part B on my schematic here. So we want to have the complex power. Now this is S with some underscore. So how do we calculate this complex power? What have we just learned hopefully in the lecture before? What is the formula that we would need to use? Yeah, but we want to, yes, the formula that you would like to write down is this one here. But this is if we look at our circuit, and if we would not have done task A before, these would not be information that we have. But information that we would more easily get from the circuit is once again our source voltage and the total current. So how from the source voltage and from the total current can we calculate this complex power? And it's a bit like here, it's more or less exactly the same formula, except that we take the complex phasor of the source voltage and we take the complex phasor of the current, and what? Yeah, and here we need to have the complex conjugate. And let's calculate this. So we go back to Octave. Oops. Go back to Octave, and now I calculate S complex. The complex S, and this is the complex source voltage and then now multiplied with the complex current. And how can we get the complex conjugate of the current?
Negative angle.
Yeah, negative angle. Yeah, but yeah, I could do this somehow by hand, but I will just use this function that is called conj for the complex conjugate. And I mean, I will calculate the result. Maybe we can try out the function. So this was the complex current. And if I take the conjugate of this complex current, what should happen? Yeah, similar results, but there should be a plus at this position. The real part should be the very same, but the imaginary part should have the opposite sign. So we get the same real part, but the negative imaginary part turns into a positive imaginary part and vice versa. Okay, so this is our complex power. I will output it once again. This is the complex power. If we calculate the real part from this complex power, then the real part will be this number. What is the real part of this complex power? Is the same as the real power. It's the same as P. Yeah, and so we had calculated P before, and this is what you meant. So if I could say, okay, it's P plus JQL. If we take the imaginary part of this, we get the same as the reactive power. And if I take the magnitude of this complex S, now what do I get then? The apparent power. So let's try this out. This was the apparent power that we calculated before. If I calculate the absolute value of this complex power, I get the apparent power. So this nicely works and fits and totally makes sense. And we can go back to the task and look, okay, we have calculated this complex power, we have calculated the real part, the imaginary part, and the magnitude, and we found out, okay, it fits to the active power, reactive power, and apparent power that we had before. Okay, excellent. Then we can go to task C that asks us what is the inductive power factor cosine phi of this circuit. And I still have maybe some few space left to write this result somewhere here in red. So the power factor cosine phi, we have calculated phi before, so we can just calculate it here in octave. And then the cosine phi is 0.707, which is 0.707, which is similar to exactly 1 over square root of 2. And this is because we had this the 45-degree angle here that I can maybe write down, and that also ds in this case is square root of 2 times p, square root of 2 times the QL. Yeah, and so the I don't know if I have a bit more space here. So the cosine phi, the power factor, could also be calculated by P divided by S. And P divided by S also gives us the 0.707, right? So this is somehow fitting nicely. Okay. So now, as we have discussed before in the lecture, this reactive power is something that we would not like to have. So let's add as it's suggested here in the task, let's add some capacitor in parallel to our load. So we have some inductive reactive power here, and then try to compensate this with this capacitor. And so there are some questions related to this. How large must the reactance or the impedance of this capacitor, or of a capacitor connected in parallel, so that the reactive power that we have here, the inductive reactive power, is completely compensated in our overall circuit then? And what is the active and apparent power of this overall circuit? So I very certainly need a new page now, and I will use maybe gray for this part with the capacitor. So what would you suggest to do now? Or what approach would be meaningful to find out how large must the reactance be or the impedance of this capacitor, so that overall and so on we totally compensate this power?
Should it just be ZL?
Well, we can try to find out. So what? So there's a suggestion, and the suggestion is that Z should just be minus ZL, right? Okay. We can try it out. Would be a lucky guess, but I mean, we don't want to compensate impedances. We want to compensate reactive power. So how could I write some equation like this for reactive power? We could say, okay, the QC should be the same as minus QL. So then we compensate the reactive powers. And so remember, we had this power triangle, and we said, okay, there is some real power pointing to the right, and then we have the inductive reactive power pointing to the top, and we had this apparent power here. And now if we take the reactive capacitive power, then this is pointing downwards. So this is the QC, and if they have the same length, then we would have this, what is mentioned here then we have complete compensation, and it's completely compensated. And this is also what this equation means, right? The QC must be minus QL. Okay, so how did we calculate the QL? We can check back. The QL was, for example, this formula or this formula or this formula, and we had the 2645 var. So I can just say this is 2645 volt ampere reactive. This is what we known from the equation before. This is the QL, and if we want to have minus QL, then of course I should have also a minus before this. So now is the question, how can I calculate the QC? How can I calculate the reactive power, the capacitive reactive power in some capacitor, in the capacitor inside the circuit? So the question is, and I think I have some space here that I can maybe use on this slide or on this page. The question is, how large is the QC? The capacitive reactive power that we have in this capacitor. And we already discussed many ways to calculate this, the inductive reactive power in the inductor, and we can check these different formulas. So the first formula included that we would need to know the current and the voltage through this element. not very applicable because we don't know the current. Then we had some equation where we would need to have only the current through this element and let's say the reactance. Also not very good because we don't know the current. But then we had a formula where we only need to know the voltage and the reactance, and then we could calculate the capacitive reactive power. So the question is, what is the voltage here across this element? It's the source voltage. It's the same voltage as we have across the source. And this is super nice. And this is also why it was so meaningful to put this in a parallel connection, because then we know the source voltage and we don't change the voltage here. We don't change what is happening here. So we still have the same power, real power and reactive power here. And we have the source voltage. So we can say we use the very same equation as here, but instead of the voltage across the inductor, we use the source voltage squared. And then instead of omega L, what do I need to write for the capacitor? The reactance of the capacitor is 1 over omega C, exactly. And so then we have this double fraction 1 over omega C, and this can of course more nicely be rewritten as omega S squared multiplied with omega C. And so now this is a nice equation where we get the omega C, or we could maybe also write it like this, because this is what the task, I think, asks us to say. This is Vs divided by Xc by the reactance. And so here, this way we get the reactance. And now we need to be a bit careful with the signs, because we said the capacitive reactive power is usually negative. So there should be a minus here, there should be a minus here. There must not be a minus here because the Xc is negative as well. Okay, so we can use this equation here. Qc is Vs divided by Xc. And I go back to my second page and say, okay, this is Vs squared divided by Xc. And yeah, then we can rearrange this equation and say, okay, Xc is the same as Vs squared divided by the minus 2000, or divided by minus QL. Let's write it like this. And this is what I can use in Octave. I just want to check. Yeah, I have the square there everywhere. Okay, so I can calculate this and say the Xc, the reactance of the capacitor that we need to have in our circuit here, is V source squared. And no complex phasor, just the RMS value, and then divided by, I will put the minus in the front, divided by QL. And if I enter, I get some result, and the result should of course be negative. Okay, I will write down minus 20. So the question is, what is the unit here? What should be the unit of this reactance? No, the farad is the unit that we have later for the capacitor. The unit of the capacitance is farad.
V over A?
Yeah, we should get voltage divided by ampere, and this is ohm. Yeah, so we should, the unit of this Xc should be 1 ohm, and it's the same as 1 volt divided by 1 ampere. And of course, we should also get it from these units here. So the unit of the voltage is volt, but we have the volt squared, and the unit of this reactive power is volt ampere reactive, which is essentially volt times ampere. So 1 volt will cancel with 1 volt, and then we get volt divided by ampere, and this is ohm. So here we get minus 20 ohm. So now coming back to the statement that we had at the beginning. How large was the ZL? The impedance the complex impedance of the inductor was j omega L, and in our case it was j 10 ohm. But now we get minus 20 ohm. So this is, unfortunately, I will take red. This is unfortunately not true. It doesn't work like this. We don't compensate impedances, we compensate reactive powers. Yeah? And why does it not work so easily this way? Unfortunately, it does not work so easily this way because we don't have the same voltages across these impedances. Here we have the full voltage, and here we just have a partial voltage, and that's why it's also different impedances at the end. If we would have no resistor at all, so if this voltage would be very similar to this voltage, then it would fit more or less, yeah. But not in this case. Okay, so we have calculated this reactance, and then we can of course also say, not in red but maybe in gray back, that now it follows from this that the complex impedance of the capacitor should be minus j 20 ohm, because it's just this was multiplied with the j. Okay, so we have successfully finished the subtask D, and we already more or less also found a solution. No, not really. Maybe not. So how to find the capacitance now of the capacitor? For subtask E, we want to find C. Where is the C hidden in the results that we got so far? Yeah, from the reactance, because we know that this reactance is minus 1 over omega C. This is what we also used on the page before here at this position, right? The 1 over omega C, we said this is xc. And okay, with the, including the minus. Oops, so I need to go to the second page. So
there's part in D we haven't solved.
there's a part in D that we haven't solved yet. Oh, what is the active and apparent power of the overall circuit? Very good point. So we need to go back to subtask D. And yeah, we want to find P and we want to find S. So how large is P? How large is S? If you look at our power triangle,
They're going to be the same.
P should be the very same as before. So it should still be 645 watt. And now the Q, the compensated Q, the total Q in our whole circuit is 0. And so if we have a power, a real power but no reactive power, the S should have the same value as P, and so it's also 2645 volt ampere reactive. And now this is the nice thing about this reactive power compensation, because if you compare with what we did before, the real power, the effective power, the active power, this stayed the same, but the apparent power went down. Before we had 3700 something, and now with the power factor correction or compensation, we just have 2600. And so we have less burden on all the cables, on all the transformers and all stuff in our power system, which is very nice. Yeah? So this is the effect of the compensation. Okay, then we can come back to subtask E here. and say, okay, this was our reactance, this is the capacitance. So if I want to have the capacitance, I just need to do 1 over omega xc with the minus to compensate for the minus of this xc, and then I can just put this into my octave here and can say C equals minus 1 divided by omega divided by xc. And then we get some result. And I will multiply this result with 10 to the power of 6. So this should be the result in micro. So 159.15. Yeah, and I will never learn to write a dot instead of a comma. 159.15. So, and then it's in micro. And then there's the question, what is the unit? It should be farad. Okay, because we calculate the capacitance. We can still check. If we check the unit of this capacitance, we take 1, then we divide by the unit of omega. The unit of omega is 1 over second. So I will add a second here on the top, because we have 1 over second, and the unit of this reactance is is ohm. Yeah, so this is just ohm. And ohm, as we have noticed here, ohm can be rewritten as volt divided by ampere. And then we get ampere seconds divided by volt, and ampere seconds divided by volt is the same as farad, because it's also the same as Coulomb divided by volt. And this is the definition how a capacitor, what the capacitance is. It's a charge stored on the capacitor, normalized or divided by the voltage across the capacitor. Remember these basic formulas that we had, not in the last semester, but in the first part of this semester. Okay, that's the required capacitance. We can see, okay, it's quite a lot already. Yeah, so 160 microfarads does not sound a lot, but it's for a capacitor, it's quite a lot. And this capacitor, of course, also because the capacitor is directly connected to our source, the capacitor also, of course, needs to withstand the source voltage. So the capacitor needs to be able to handle the 325 volts and then plus some plus something, because in the mains power grid you might have over voltages due to surges and bursts and lightning strikes to the power grid and switching events with motors and so on and so on. So yeah, building this at the end, this will be a quite large capacitor. Yeah, it will be really, I don't know, maybe like my, usually capacitors of course are round, but it might be even more than the size of this box. If you have a capacitor with 160 microfarads that can withstand 230 degrees of RMS voltage and the associated peak voltage and so on. Okay, and the last task we have by accident already done, draw the corresponding power triangle. It's more or less this one. Yeah? And the compensated, or the Q total, it's because we did the full compensation, is just very small. It's not really some error, it's some small dot somewhere. But real power, reactive power of the inductor, negative reactive power of the capacitor, total reactive power is 0. And here we have also the phi angle that we had before. And so the compensated phi angle is also 0, because we have no reactive power anymore after the compensation. So this, I think, is a very nice solution of this task, of this exercise, also with some quite nice number crunching complex calculation here in Octave that I would not by any chance like to do on a usual calculator, but only in a mathematical software like this. And yeah, which questions are still open?